As these images begin to cycle, I want you to notice something that may feel familiar. These are the futures we keep imagining, whether we consciously dwell on them or not. They are the stuff of our dreams. For decades now, we have drawn them, modeled them, simulated them, and embedded them into our culture. Through books, films, and formal studies, we have planted the seeds. Long before we could articulate it in technical terms, many of us had formed an intuitive picture of where humanity was headed, into space. What you're seeing here are not mission concepts. They are not isolated events, flag planting exercises, or brief excursions. They are representations of civilization continuing beyond Earth, places where people work, play, and grow over long periods of time. The specific details vary. The architecture changes, the artistic style evolves, but all of these visions, however, there's one shared and most often unspoken assumption: scale. All of these futures assume permanence. They assume industrial scale logistics and throughput. They also assume that space is no longer something we visit occasionally, but something we operate within continuously. To make this concrete, let's focus on one deliberately modest example. This rotating wheel station is very much in the lineage of early orbital concepts and was never intended to be a megacity. It is a transit hub, a hotel, an essentially routine infrastructure designed to feel ordinary rather than heroic. And yet, even something this restrained, something meant to represent normalcy rather than ambition, would weigh tens of thousands of metric tons once fully constructed. That number is important, not because it is extreme, but because it is conservative. It represents the minimum scale at which humanity stops being a series of missions and starts resembling a functioning environment. Once you let that register, the realization begins to emerge. These visions are not demanding because they are extravagant or fanciful. They are demanding because they are ordinary. They describe what happens when humanity stops visiting and as an occasional endeavor and begins to operate in a matter of course. That distinction between visiting and operating is where the rest of the conversation begins. When we talk about humanity in space at scale, it's important to be precise about what that phrase actually means, because it's often used loosely and is frequently reduced to a question of cost. In most contemporary conversations of launch, the dominant metric is cost per kilogram to orbit, and it's an understandable focus. It remains a useful one. When launch was rare and exceptional and extraordinarily expensive, reducing cost per unit mattered a great deal. Cost per kilogram, however, is not the metric that determines whether a civilization can function in space. Civilizations are not constrained by the price of individual shipments. Although cost does matter, they are constrained by throughput. What matters is not how cheaply you can deliver a single kilogram. It is how many kilograms can you move year after year reliably, without extraordinary effort, without exceptional permissions, and without cumulative damage. Once you shift the frame from missions to operations, the relevant unit stops being dollars per kilogram and becomes kilograms per year. A megaton, or 1 million tons, seems like an incredible number, but for industrial applications, it's used regularly. Shipping, energy, mining, and construction routinely use masses in the megaton range, and we move scale routinely with incredible efficiency here on Earth. The infrastructure that performs this is largely invisible and completely taken for granted. Space currently feels different because we treat it as exceptional. Civilization does not grow by exceptions or exciting one-offs. It grows by boring repetition day after day. To lift a megaton annually would mean putting approximately 2,700 tons into orbit every day of the year. That's the equivalent of a full-size modern freight train and cargo. That is not a launch campaign, it is an industrial supply chain. And it immediately raises questions about environmental carrying capacity and social acceptance. In contrast, we saw just moments ago, the ISS is a roughly 420 tons, and it was assembled over many years and dozens of launches. While this is a triumph, no doubt, it also illustrates the throughput limits we face and continue to face as newer, better, cheaper rockets come online. New rocket launch capacity is welcome and necessary, but when traditional rocket cadence increases, so does local resistance. Not in my backyard is not a theoretical issue. It's a real-world constraint that becomes more difficult, not less, as operations intensify. This change in perspective has a profound consequence. The futures we just looked at, orbital habitats, large-scale manufacturing, permanent infrastructure, they're not compatible with thousands of tons per year, or even tens of thousands. They imply flow measured in the hundreds of thousands and ultimately millions of tons annually. That is what civilization scale logistics looks like, whether it takes place on Earth or not. When you examine current launch systems through that lens, a hard constraint becomes visible. Chemical rockets, even highly refined and partially reusable ones, remain fundamentally episodic systems. In this context, episodic means discrete, high-entropy launch events which have cumulative environmental effects. Rockets are powerful, but they are not continuous. Individually, they are impressive, but they are not scalable in the way that railways, ports, or power grids are scalable. This is not a criticism of rockets. It is simply an acknowledgement of what they are optimized to do. Rockets excel at overcoming gravity in discrete events. They carry delicate payloads, people, and large monolithic objects. They do not naturally lend themselves, however, to sustained, high-cadence industrial transport. At civilization scale, that distinction matters. If the futures we imagine require moving mass in volumes measured in the megatons, then any system that remains finite and episodic will eventually become a bottleneck, regardless of how efficient or well-engineered it may be at smaller scale. Once the realization is on the table, discussion changes. The question is no longer how to make individual launches slightly cheaper or slightly better, but whether the underlying architecture is capable of supporting continuous delivery of mass off of Earth at all. That's the problem of scale we need to confront before anything else. Once the question is framed in terms of sustained throughput rather than individual missions, a second constraint becomes impossible to ignore: cadence, the frequency at which launches must occur over long periods of time. Shipping ports do not operate occasionally. Power plants gain their utility precisely because they are always on. Civilization-scale systems are defined not by peak burst capacity, but by boringly reliable throughput capacity. Moving material at civilization scale does not just require moving a great deal of mass. It requires doing so frequently, predictably, and over long periods of time. Cadence is where the conversation about space launch quietly collides with the realities that are often treated as secondary. Environmental impact is one of those realities. Much of the public discussion around launch focuses on the effects of individual flights, as though the environmental footprint of space activity can be evaluated one launch at a time. But the framing breaks down completely once you begin to talk about scale. Environmental impact does not scale with ambition, it scales with repetition. Chemical rocket exhaust is not simply a localized plume that disperses harmlessly. The byproducts of combustion interact differently across layers of the atmosphere, and some of those interactions are in regions where the natural clearing process is slow. Compounds such as nitrogen oxides, carbon dioxide, and black carbon soot formed during ascent can persist longer than most people realize, especially when deposited at high altitude. At today's launch rates, these effects are dismissed as negligible, and they are, but that dismissal is only possible because cadence is currently extremely low. If launch activity were increased by 3, 4, or 5 orders of magnitude to support continuous industrial activity in space, the cumulative effects would no longer be abstract or ignorable. They would become the defining constraint. This is where the idea of green rockets falls apart. Green only gains credibility because of our low cadence environment. At high cadence, however, none of the traditional rocket designs could be considered green. The question is whether an entire launch architecture can operate at high frequency without placing unacceptable stress on the atmosphere and the biosphere that support Earth. There is also a social dimension to this constraint, and it is just as real. Launch sites are not abstract points on a map. They exist in political jurisdictions, near communities, under regulatory regimes, and within ecosystems. Even today, with relatively modest launch rates, spaceports face growing resistance from nearby populations, increasing scrutiny from regulators because of the noise and the safety zones and the emissions and land use become points of contention. These pressures do not diminish with scale. They intensify greatly. Human tolerance has a saturation point, and like all systems with limits, behavior changes dramatically once the saturation point has been reached. Modern terrestrial infrastructure projects have failed because the communities where they were overwhelmed. This is true for highways, ports, pipelines, and will be true for spaceports as well. Any system that aspires to move megatons of material off of Earth must therefore satisfy a requirement that is rarely stated explicitly. It must be environmentally compatible and acceptable socially at high cadence, not as a special exception, but as a routine mode of operation. This requirement dramatically narrows the space of viable solutions. Once you accept that cadence, environmental impact, and social acceptance are not peripheral concerns, but are central constraints, many otherwise impressive launch concepts quietly remove themselves from consideration. The problem is no longer simply one of engineering and performance. It becomes a systems problem involving physics, chemistry, ecology, and human tolerance. It is within this tightened constraint space that the rest of the discussion takes place. When environmental impact and cadence are treated as a first-order constraint rather than a secondary consideration, it becomes clear that the problem we are facing is not one that can be solved through incremental improvement. This is not a new situation in the history of large-scale infrastructure. We as a species have encountered exactly this before. In the early days of industrial transport, steam locomotives were a breakthrough technology. They dramatically increased the speed and volume at which goods could be moved, and for many decades, improving steam engines was the correct path forward. Engineers made them more powerful, more efficient, more reliable, and safer, and every one of those improvements mattered. But there came a point where further refinement no longer addressed the real limitation. If we attempted to move the volume of freight that modern civilization depends upon using steam locomotives, the results would be catastrophic. Cities would be choked with soot, rail corridors would be lined with ash, air quality would collapse on a regional and eventually global scale. The issue would not be incompetence or lack of effort, it would be architecture. The transition to diesel-electric rail was not about squeezing the last few percentage points of efficiency out of steam. It was an architectural phase change. Decoupling the energy source from the mechanical act of transport, diesel-electric systems enabled vastly higher throughput, far higher cadence, and dramatically reduced environmental impact per unit of cargo moved. This transition is what made modern freight logistics possible. Chemical rockets have been refined to an extraordinary degree. They are powerful, reliable, and astonishingly capable machines. Their continued use for exploration in human spaceflight and specialized missions is not in question. But when evaluated as the backbone of a continuous industrial scale or orbital logistics operation, they face a limitation that cannot be optimized away. Like steam locomotives, rockets release a large amount of energy in discrete localized event. That works well when cadence is low and missions are infrequent. As cadence increases, however, the localized environmental operation costs begin to dominate. As noise, safety buffers, exclusion zones expand, public tolerance diminishes. while demand for regulatory pressure increases. Reusability improves economics at the margins, but it does not change the character of the system. Refurbishment is not free, and the ground infrastructure remains complex and resource intensive. The environmental impact of repeated launches accumulates regardless of how efficient individual vehicles are reused. This is not a failure of execution, it's a consequence of architecture. At civilization scale, what matters most is not whether a system can perform exceptionally in isolated events, but whether it can operate continuously without unacceptable side effects. Just as steam locomotives could never have supported modern freight volumes without poisoning the environment, traditional rocket architecture cannot support megaton scale to orbit, and without running headlong into environmental and social limits. History suggests when these limits are reached, further optimization gives way to replacement, not because the old system failed, because the scale of the problem has changed. That is the transition we are facing now. Once we accept that civilization scale activity in space requires sustained high cadence movement of material and that environmental and social constraints are non-negotiable, it becomes tempting to conclude that something new is needed and that anything new must therefore be sufficient. History suggests that novelty alone is not a solution. Periods of architectural transition are often accompanied by a surge of alternative proposals, many of which correctly identify the problem but misjudge the solution. Space launch is very much in such a period now. Over the past several years, a number of organizations, both public and private, have announced efforts to move beyond traditional chemical rockets, particularly for the first stage. This includes work on electromagnetic acceleration, ground-based launch assist systems, and large spaceplane concepts. The activity itself signals the underlying constraint is widely recognized. The challenge lies in execution. Before examining why many of these approaches fall short, it's important to be clear about something. Chemical rockets are not going away, nor should they. They remain the right tool for specific classes of payloads, people, biologics, delicate instruments, and certain monolithic components that cannot be easily modularized. These payloads impose limits on acceleration, vibration, and handling, make traditional rockets not only appropriate, but necessary. The problem is not that rockets are inadequate. The problem is that they are bounded. Even at high cadence, much higher than exists today, traditional rockets will always face localized environmental and operational limits that prevent them from supporting the continuous movement of material of bulk material at megaton scale. With that distinction in mind, we can look more clearly at some of the proposed alternatives. Many electromagnetic launch concepts focus on railguns or coil guns, borrowing technology and terminology from laboratory-scale devices or military research. At first glance, these approaches appear attractive. No onboard propellant for the first stage, direct electrical energy input, and potentially high efficiency. In practice, limitation of these approaches becomes a source of fundamental scaling problems. Railgun architectures rely on physical contact between the payload and the conductive rails under enormous current and force. At the velocities and repetition rates required for launch, friction, rail erosion, and structural deformation become the dominant failure modes. The rails themselves will warp and degrade. The acceleration distances quickly become impractical. The velocities and payloads that are required can't be supported. And not knowing this important detail has led many teams to go astray. Coil guns avoid direct contact, but introduce a different set of limitations. Remnants, inefficiency, and inductive heating grow rapidly as power levels increase. The projectile still maintains contact with the launch tube and experiences similar erosion as does a railgun. Scaling becomes a huge issue, and thermal management begins to dominate system design. As mass and velocity increase together, overall efficiency tends to degrade rather than improve. More broadly, any acceleration architecture that relies on sustained surface contact or tightly coupled electromagnetic interaction faces compounding losses at scale. These losses do not remain secondary, they become defining. The cube law bows to no one. Large spaceplane concepts introduce another class of false comfort. By scaling vehicles upward and attempting to integrate multiple functions into a single platform, they run afoul of basic scaling laws. As vehicles grow, mass and surface area outpace available power and structural margin, while thermal stress and operational fragility escalate. The result is frequently a system that looks elegant on paper, but becomes increasingly constrained in practice. What all of these approaches share is not a lack of creativity or ambition, but a tendency to underestimate how unforgiving scale can be. Identifying the need for a new paradigm is only the first step. The harder task is finding an architecture that remains efficient, durable, and environmentally compatible as cadence and throughput increase together. In periods like this, many ideas appear plausible. Few will survive scrutiny, and only a very small number will remain viable once all the constraints, physical, environmental, and operational, are applied simultaneously. This narrowing is not a setback, it is a process by which real infrastructure emerges. If the previous sections narrowed the solution space by constraint, this final section is about broadened vision. What does civilization scale transport actually look like? The first thing to notice, it does not look heroic. At scale, space activity stops being dominated by singular vehicles or bespoke missions and begins to resemble logistics. It becomes repetitive, modular, and deliberately boring in the same way that ports, rail yards, and warehouses on Earth are boring. That boredom is not a failure of imagination, it is a sign that a system has matured. One of the key enablers of that transition will be standardization. Rather than designing, oh darn it, I did it again. Unbelievable. Sorry, guys. There we go. Rather than designing each vehicle, rather than designing each payload as a unique object that requires special handling, large-scale construction favors modular cargo units, sized to balance human and robotic handling, structural efficiency, and operational simplicity. In this framework, a payload of 2 tons is not a limitation, but a feature. A 2-ton cargo module can be manipulated in zero-G by a single person and can be more easily manipulated by space robots. Once cargo is modular, other elements flow naturally. Standardized interfaces for docking and integration simplification, and robots, lots and lots of robots. Tugs can move materially efficiently between orbits without tying the launch system to a specific destination. The important point, I don't know why I keep saying that. The important point, what is that? I'm not touching anything. Okay. All right. The important point is that launch is no longer asked to do everything. Its role is simply to deliver material into the logistics network and to not place each object precisely where it will ultimately reside. This decoupling is what allows cadence to increase without multiplying complexity. When systems are designed this way, the distinction between different transport modes becomes obvious rather than ideological. High-value, delicate, or human cargo continue to follow paths optimized for care and control, while bulk material follows the path for throughput and efficiency. Each is used where it makes sense, and neither is forced to be something it is not. This is the context which orbital bridge should be understood. Orbital bridge is not a vehicle. It is not a replacement for rockets. It is infrastructure designed specifically to address the bulk transport problem that emerges once scale, cadence, and environmental compatibility are treated as non-negotiable constraints. Its purpose is to move large quantities of durable material into orbit continuously with minimal localized environmental impact, and do so in a way that integrates cleanly with orbital logistics. Orbital bridge is always on. It operates 24/7, 365, except during the most severe weather. 400 megawatts of electric power gets you a launch every 15 minutes. 2 tons every 15 minutes, nonstop, gets you 70,000 metric tons to orbit every year of operation. Double the power, and it's relatively straightforward to create a second rail. Multiply a 2-rail installation times 10 around the world, and you have a launch capacity at 1.4 megaton annually. Orbital Bridge is something new. It represents a clear path to megatons, using only electricity and pure water as inputs, leaving only pure water vapor as an exhaust. Environmental degradation would be greatly minimized compared to attempts to use traditional rockets to lift a similar amount of mass. Preserving the environment and being a good neighbor will make not in my backyard less of an issue. Because it is infrastructure, its impact is multiplicative rather than additive. A single installation establishes the baseline flow. Additional installations replicate that flow. The result is not a dramatic one-time achievement, but a steady increase of capacity over time. At this point, the conversation changes again. As we have seen, the limiting factor is no longer whether a particular mission can be afforded or permitted, but how quickly civilization will build out the supporting infrastructure. Will it be years, decades, or never? The outcome is directly related to the effort and resources devoted at the outset. This is not a claim about inevitability driven by optimism. It's a claim about what follows when constraints are respected and systems are designed accordingly. The constraints of the status quo are obvious, regardless how often they are swept under the rug. Eventually, reality will win out over dreams of tens of thousands of giant rockets every year. The future images we began with stop being speculative once the logistics beneath them exists, and it becomes a natural consequence of operating in space at scale. I appreciate you taking the time to listen to my speech. If you guys have any questions, I'm going to go off to the side over there, and you guys can ask me questions or learn about Orbital Bridge or just chat. Thank you very much for your time.